Alright, this will be a quick video on how to build from metallic atoms, covalent compounds. Ionic compounds we know are nonmetals with metals, but we're making our covalent compounds. Those that have sigma bonds, or shared electrons, pi bonds. Covalent, meaning nonmetals are coming together to share 2 electrons between 2 atoms at least, and you can have double bonds where they share 4, but again the idea is sharing. And then we're going to use to make those some Lewis structures, and there are rules for drawing Lewis structures. And then we're going to move to VSEPR, valence shell electron pair repulsion theory, for how to shape what we just drew. So you're kind of moving through sort of a line, what nonmetals are getting together, how can they make a covalent compound. There's some rules for that in drawing Lewis structures, and we're going to shape it according to VSEPR. And then one last thing is we're going to look at bond polarity and molecular or overall polarity. What that means is kind of having regions where partial negative or electrons are kind of rich towards one side of a bond. Let me just give you the classic one, maybe a carbon-fluorine bond. The carbon is not as electronegative, so this bond tends to cheat towards the fluorine because it is more electronegative. Things like that are what we call bond polarity, and that leads to an overall molecular polarity for the whole structure. And that is important finally into kind of phase behavior. How does it behave as a liquid? How long will it be a liquid? If you heat it up, will it go right to gas? So all that said, this video is going to go through probably the first part just up to VSEPR. The last part, and the next 10 minutes will be from structure. How can we get all the way down to what's it look like in a liquid? How does it, what's its boiling point? A lot of that's going to be determined by the molecular polarity, which is part of VSEPR, because you got to know the shape before you can determine the overall polarity. So a lot going on here. I hope that kind of helps as a sort of an outline on where we're going with these 2 videos. The first one, again, is just going to deal with how do we take nonmetals down to a structure and shape. So we always, think about connectivity. That's kind of where we need to go. Lewis structures, there are rules for how things connect when it's nonmetals. First of all, we need to determine the number of valence electrons. It's going to kind of bleed through, I think, on the other side. Not too bad. So determine the valence electrons, determine the atom of greatest need. Which atom needs to have more electrons or bonds around it? Draw the frame around that atom of greatest need and fill in with electrons from the outside to the inside. And we'll talk about what that means. But as you have a atom of greatest need and you framed around it all the other atoms, you'll put electrons in from the outside in. And then drawing and understanding Lewis structures. This is getting into the VSEPR part of it, valence shell electron pair repulsion theory. We define the shape, we determine the electrons, the number of electron groups, they call it, number of lone pairs and number of atoms off of the central atom. So that's going to lead us into bond polarity and overall polarity, but we're going to probably have to stop, I don't want to make these videos too long, somewhere around VSEPR, just before it or just after it. All right, first, there are Lewis structures or Lewis symbols for just the atoms. We need to know how many valence electrons you have for your atoms to start with. So boron, for example, is in the second row. It's in the 3A. It's 3 steps over lithium, beryllium, boron. So we can say boron has 3 valence electrons. You can start drawing the dots, make sure to work around from one side to the other. So we could represent boron like this. It doesn't matter. You could have had, instead of the dot here, you could have the dot here. Now carbon is the next step over. So one side, another side, another side, another side. You have 4 valence electrons. And you guys get the idea. Nitrogen would then have 5. Now this one's going to have to come back around. So we'd have 5 valence electrons. You can go further, and there's a video. If these notes are made available in PDF form, you can check it out on how to do Lewis symbols for atoms. So that's the gist of it. Count the number of steps to the atom. We had for boron 1, 2, 3. And that's the number of dots or electrons that are owned, valence electrons that are owned by that atom. They're going to be used for bonding. Right, next, I guess, sort of step is to draw the Lewis structures, reaching a goal of a filled valence shell. So H, hydrogen, has 1 electron, but he doesn't want to have 8 around him. He would be like helium if he just has 2. So he wants to have just 2 dots around him. Bromine, though, needs 1 step to be like, I guess, either xenon or I think xenon, the next one down from argon, or yeah, from neon. So it is argon. No, it's xenon. Sorry, just trying to think of my noble gases that are next to bromine. So 1 step over, he only needs 1 bond. So we bring that 1 dot here together with this 1 dot, and you get a bond. So the number of valence electrons now around bromine would be 8, because he's bonded to 1 hydrogen. You can play the same game. Sulfur has 2 steps away from the nearest noble gas. He needs 2 bonds to get to 8. Nitrogen, 1, 2, 3, I guess, unpaired electrons. Now what he's going to do is bond to another nitrogen and bring his 3 unpaired with this one's 3 unpaired, and you get now 6 in the gap. There'll be a triple bond. But in general, again, we still have 8 around this nitrogen because it's sharing these 6 in the middle, and these 8 are around this nitrogen. So we are hitting a point where we stop drawing our bonds around an atom when we get to a filled valence shell. So you can play this game with a lot of different structures. We can have oxygen. We know it bonds twice to get to a filled valence shell. To do that, then, the number of bonds he needed was 2. Nitrogen, he has, again, need of 3 more electrons to get to 8. He does that through sharing with these 3 hydrogens. So it's 3 to get to that 1, 2, 4, 6, 8. And we draw the 2 dots here on nitrogen because that's the lone pair that did not bond. A lone pair of the 2 electrons that were not used for bonding. You call them non-bonding electrons also. Last is carbon. He needed to make 4 bonds, so he can get to 8. Now over on the right here, let's just have an example problem. What is the number of steps from carbon to neon? So I hope you're counting with your periodic table. You'd count from carbon to neon, and it would be 4. So it needs to make 4 bonds. What's the number of steps from hydrogen to helium? It's 1. Each hydrogen then only makes 1 bond to get to not an octet state, but to like a noble gas state too. So we bring in 4 hydrogens, making a single bond each with each hydrogen because they only want 1 more electron, and we would get what's called methane. This is the Lewis structure here that we have shown with lines instead of dots. If you see it like, I guess, in this form here, this is a Lewis structure where they're showing the bonding electrons, those 2, as dots instead of a line. It's I guess, satisfactory to the rules for Lewis structures to show it as dots, but you'll soon find it's easier just to show the dots as lines. So instead of having 8 dots around this carbon, you can just say, if the dots are used for bonding, we'll show it as a line. So that's also, I guess, allowed for drawing of Lewis structures. Okay. Well, we'll go ahead and do about 4 more slides and stop there. Sometimes atoms have more or less bonds than what they really want. So that's going to give them a formal charge. So for example, nitrogen likes to have 3 bonds off of it. Here we only see 2. 1 bonding pair and another bonding pair to, let's say, hydrogens, for example. If that's the case, it's always going to have a negative charge if it has 1 less bond than what they really want. So oxygen likes to have 2. He has 1 less bond. He's going to be negative. Of course, if it's the bonds they like, 3 and 2, he's neutral. If they have more bonds than what they typically, this is just true for nitrogen and oxygen, they'll have a positive charge. 1 more bond than what they typically want, they'll be positive. There's more on formal charge. We'll probably have to talk about in class some formal, I guess ironic, formal rules for formal charge. But remember the N's and O's. It's really helpful just to think, Does it have one more bond than what it wants? It's positive. It does have one less bond, it's negative. All right, so covalent bonding, we know, is sharing. Carbon needs 4 bonds to get to octet state. N is 3, O is 2. H and F, it's just 1 bond each. So just to kind of summarize how you've played this game of building a Lewis structures, figure out who has the greatest need. Find the middle. Who's going to be in the center of all the bonding. Build the frame around it just with single bonds at first, going to the outside. Add in lone pairs from the outside in. That's really important. And then we'll see this number 4 as we talk about resonance. Drop down lone pairs if needed. So let's do this one example and stop here. This is about a 10-minute video. So example CO2. If I were to give you CO2 as a formula and say build the structure, carbon would be in the middle. Why? Because he needs 4 bonds. So you could play this game, and I'm just going to show it here. We have C in the middle, and oxygen to either side, and a bond, 1 bond to each of those. So now we can say, well, I framed it. We built the frame around the center. We do need to know the total number of electrons that have to go in. So at some point, you got to figure out the number of valence electrons. So I'm going to do that on the frame here. The O needs 6, or sorry, it has 6 electrons. He needs 2 more. Carbon brings to the bonding game 4, and this other oxygen brings 6. That's a total of 16 electrons that are going to have to be used to make the structure for CO2. Now I've already used, and you say, well, what's this 6 plus 4 plus 6? That's our 16. What's this minus 2 times 2? Well, we've already put in 2 bonds, so that's 4 electrons. So from the outside in, I'm going to put 12 more. 2, 4, 6 on one side of this oxygen, 2, 4, 6 on the other side where this oxygen sits, and that's now 16 E's. And you say, well, how do you know? Well, 2, 4, 6, 8, that's a bonding pair. 2, 4, 6, 8, that's another bonding pair. 8 plus 8 is 16. But we notice carbon's not where it wants to be. It wants 4 bonds. So what we're going to do is drop down to the middle, these 2 electrons, do the same thing over here, and we would now have a double bond on the left and a double bond on the right, and the dots that I used that were non-bonding are now down in the gap. The electrons, again, that are non-bonding here are down in the gap. So now carbon is happy. Oxygen wants to have 2 bonds. It's happy. And we have our final structure. I'm going to stop there. We'll pick it up with the next video, kind of building from this.